This is the video that is the introduction to complex numbers. I've done videos about complex numbers before, and I will put everything in a playlist and link it in the description here. But in the other times, I was saying this is not an introduction. I'm already assuming that you know the basic facts about complex numbers, and then I just wanted to do some specific questions or comments. But today we are actually going to do an introduction to complex numbers. So I'm assuming you've never seen them before. Maybe you have if you're searching for a video about this, but pretend you've never seen them and let's go from the beginning. I'm going to start by saying some things about other numbers, real numbers, and then I'm going to work my way towards complex numbers because I want to make sure that you see how they fit into the big picture. For this, I want us to be thinking about the real numbers not individually by themselves, but as a whole line of real numbers, and then that you're going to single out one of those numbers and use it to do an operation, but not to another number on the line. You're going to do an operation to the whole line, and then we're going to observe the different effects that this operation can have on the line. When you add a number to numbers, they all move together to the right. So if you do plus 2, everybody comes over here. And then if you do, say, minus 4, we're going to go to the left. When you multiply by a number, like doing times 2, for example, everybody stretches out. The positive numbers become bigger and they go to the right, while at the same time, the negative numbers are becoming more negative to the left. And then if you multiply everybody by a number that is less than 1, the opposite happens in the stretch. Everybody's going to become smaller, everybody coming closer to 0, but again, the same thing happening to the right side and the left side. But when you multiply by a negative number, if you multiply by -1, the positive numbers want to go to the left and the negative numbers want to come to the right. So they are going to be reflected like this. It's weird that I had to come out of the wall in order to do the reflection, but what's important is the beginning position and then the ending position, which has everybody backwards. But since what matters is the beginning position and the end position, not how we got there, there is another way to get from here to there without having to get out of the wall, right? We could come this way. So we took a different path to get there this time, but we got to the same place. The 1 is now in the -1, the 2 is now in the -2, and the negatives have come to this side. The -1 is on the 1, the -2 is in the 2. But the advantage of getting there by rotating instead of reflecting is that if we want, we don't have to rotate all the way. We can stop halfway, for example. And now it's looking like a coordinate plane because you have two directions, horizontal and vertical. So we've always thought of numbers as either translations or stretches. And the only thing that I'm asking you to do different right now is to also think of them as rotation. But in order to do that, we're going to need some new numbers because all of the old numbers were already either doing translation or stretches. So if somebody's going to do rotation, it's going to have to be somebody else. So I want to begin by thinking about this half rotation that we just did. Of course, it didn't have to be half. We could have rotated any amount that we wanted before getting to the other side. But I want to think specifically about the half of a rotation. So when you do two of these things, one after the other, you're just multiplying them, right? So if you stretch by 2 and then you stretch by 2 again, that's just 4 because it's 2 times 2. And the same thing is happening here. We are multiplying by some number which got us here, but then if we multiply by it again, we're going to get there, which was the multiplication by -1 that we previously knew as reflection. So we have some number, we're going to call him I, that if you multiply by I and then by I again, you're actually just multiplying by -1. That means that I to the power of 2 is -1, which in turn means that I is the square root of -1. And then don't get nervous because the square root of -1 never existed before. It's doing something that we've never done before, which is rotating only halfway. So it's okay that it was never there before, but it's there now. We're going to say that this number is here on the vertical axis, okay, because it was a rotation that brought our number line here. And I'm going to make everybody look a lot smaller now. I've actually decided to zoom in on my axis a little bit now so that you can see everybody a little bit better. And since we were talking about half of a rotation, how about we try now to talk about an even smaller rotation? Let's just go 1/4 of the way there. What I'm drawing here is a circle, okay? Because as you take the number that was originally in the horizontal line and you start rotating it, that's the path that it's going to take. It's a circular path until it gets there. So if you only go halfway until the vertical axis, that means that you're multiplying by a number and you need to multiply by the same number again in order to even get to I. So that would be the square root of I. But from what we're seeing in the picture, we also know the coordinates of that point. That is a point in the circumference of a circle of radius 1. It started as 1 here and just rotated. And it's like the diagonal of a square, right? This is a right triangle, has 45 degrees here, 45 on the other angle as well. And then this is just basic trigonometry. The measure of the sides of the square that has a diagonal 1 is 1 over the square root of 2. So I'm putting the 1 over square root of 2 coordinate here, but over there I actually want to multiply that by I, just to say that that's a vertical coordinate, okay? The original numbers are going to be in the horizontal, and then these new I numbers are going to be vertical. This is 1 over root 2 in the sense that it's this length, but because it's vertical, it's 1 over root 2 times I, which I am writing as I over root 2. So it's looking like the square root of I is this ugly looking number. Let's confirm that with a calculation. In order to check if something is the square root of something else, you take that number and you square it and hope to find I in this case. We're going to use the special product here, right? So first, this fraction squared is 1 over 2, and then we have plus 2 times one fraction times the other fraction, and now this fraction squared, well, the denominator is going to be 2 again, but the numerator is I squared, which we were talking about before, is negative 1. So a lot of things are going to cancel out here. Half minus half, and this 2 cancels out with the 2 in the denominator here. The answer is just I, like we wanted it to be. So I did this little check before explaining why I am adding these two numbers instead of considering it as a point with two coordinates written with parentheses, 1 over root 2, comma, and then I over root 2. So I wanted you to at least have some reason to believe that adding is the correct thing to do, because at least this is working. But everything else is going to work too. Plus is going to continue to be translation. Plus has always been translation, but when it was plus a positive real number, we were going to the right, plus a negative real number, we were going to the left. And now when we do plus I, we're going to translate up, which is exactly where this number is. You can think that it was the 1 over root 2 that got translated up by I over root 2, or you can think that it started here at the I over root 2, and then it got translated to the right by adding 1 over root 2. Either way, you can get from the origin to any point by doing two translations, one horizontal and one vertical. And that's why for the numbers on the plane with two coordinates, it's always going to be one horizontal number plus one vertical number. When we have variables in this number plane, we usually refer to them by the letter z instead of x. So what I'm saying is that we can write any number z as a plus bi, where I is exactly this number. A and b are real numbers. They are the amount of horizontal translation in the case of A, and B is the amount of vertical translation, and Z would be represented by a point with coordinates A, B. So this is very good for translation, but multiplication works very differently than that. Coming back to the real numbers, which are just horizontal, I mentioned that multiplying by a positive number bigger than 1 is a stretch this way. Multiplying by a positive number less than 1 is stretching this way, and multiplying by negative 1 was this, a reflection well, now we're thinking of it as this, a rotation, but it's the same thing. The point is that when we were talking about that, I didn't say anything about multiplying by -2, for example. And that's because -2 doesn't do anything new that the other numbers weren't doing before. When you want to multiply by -2, you're just going to first multiply by 2 and then multiply by -1. So you're doing both things, even in the real numbers. So here we are going to need to do two things as well in order to multiply by an arbitrary number on the plane. The first thing is rotation, like we were just talking about here. And the circle that I drew in blue here is a special circle because it's a circle of radius 1, and multiplying by 1 doesn't do anything. Multiplying by 1 is identity. So when you want to multiply by one number that is on this circle, such as this one that we used as an example, then that's just rotation. There is no stretch attached to that. But say you were interested in that number, 1 plus I. So it is on the same line as the previous point. It has the same angle here, but the red point belongs to a slightly larger circle. It's a circle of radius the square root of 2 because it is the diagonal of a square of side lengths equal to 1. So say you started at the number 1 and then multiplied by the red number. Well, 1 times red is just red, right? So you come here. You did this little bit of rotation, but you also moved to a different circle because the number 1 belongs to the blue circle. And then from here, if you want to multiply by 1 plus I again, you're going to have to do both of those things separately. First, you're going to again do another rotation of 45 degrees, thus making it vertical. But as for the radius, when you multiplied it the first time, you left a circle of radius 1 and multiplied that by the square root of 2. Now you're going to multiply by the square root of 2 again, getting you to a circle of radius 2. So now I guess we should check if 1 plus I squared is equal to 2I. So let's use this special product again. 1 squared is 1, plus 2 times 1 times I is 2I, and then plus I squared is -1. So we're going to be adding -1 here, which cancels out with the 1, and the answer is 2I, exactly like we wanted it to be. The only thing is that it is a little bit problematic to have to do this every single time we want to multiply two numbers. The special product is annoying. It is a thing to do, and then 2 terms become 3 terms. I would just rather not do that if I don't have to. So let's look at our numbers again. And remember that when we were adding numbers, it was all about horizontal translation and vertical translation. But when we are multiplying numbers, it is about how much we're going to stretch and how much we're going to rotate. And the things that are telling us about these two movements are not the A and the B. The number that is telling us by how much to stretch is the radius of the circle in which the point is. And the number that is telling us by how much to rotate, it's the angle between the horizontal line and this other line that goes from the origin to our point. So you're just adding angles. You started at 0 angle, and then you're going to multiply by red. You're going to go to 45. Multiply by the same point again, it's another 45. If you did that again, well, plus 45 degrees again, and so on. The stretch that is given by the radius is multiplication, as all stretches are. But the rotation is addition. You're adding the angle. And all of this put together means that it would be convenient to have another way of writing a number that made mention of the radius and the angle instead of these coordinates A and B. So let's go back to trigonometry again and look at our number, the square root of I in the blue circle. The blue circle is actually the unit circle, right? So you have cosines on the horizontal, you have sines on the vertical, and the coordinates of the point on the unit circle, if you go here, this is just the cosine of 45 degrees, and the vertical coordinate of the point is going to be the sine of 45 degrees. So I can write it like that if I want, and it looks a little bit clumsy and long at first sight, like why would you do that? But the reason is what I was talking about. It looks longer and uglier, but now it's making reference to the radius and the angle, which are the things that I'm going to want to focus on when I want to multiply numbers. So again, when I want to add numbers, I'm going to be focusing on this. But when I want to multiply, this is going to be more convenient because these are translations and these are rotations and stretches. Although really, they're both just saying the same thing twice. R cosine theta and r sine theta are just the coordinates of the point, just as much as A and B. The cosines are the horizontal coordinates and the sines are the vertical coordinates. And this already takes care of a lot of questions about complex numbers. Sometimes it all comes down to knowing what is the best way to talk about them, depending on whether you want to add them or multiply them. If you want to add them, you're going to use the Cartesian form and just add the real parts and add the imaginary parts. But if you want to multiply them, then you're going to use the polar form and multiply the radius and add the angles. Again, you're multiplying these because the radius are making stretches, and you are adding angles because the angle is telling you how much to rotate. So if the first number, z, is telling you to rotate theta, and then the second number, w, is going to tell you to rotate another alpha, so you just start from where you were at theta, and then you rotate another alpha, making the total angle theta plus alpha. Did you notice that it took me a really long time to start saying the actual names of these things? Complex numbers, real part, imaginary part. One of the reasons that I did that is that I don't particularly like those names. I'm not suggesting that we not use them. Of course, I'm going to use the names. I'm just saying that I have things against these names because, first of all, when you say complex numbers, you immediately create a reaction of like, this is difficult. I am not smart enough to handle these. Because complex can be translated as complicated in a lot of people's minds. Of course, it's not meant to be. It's just trying to reflect the fact that in order to talk about one number, we now have to give two coordinates. So it's complex in the sense that it's built up of two smaller parts. And the word imaginary I like even less, especially when contrasted with the word real for the numbers that are in the horizontal line, because it creates a reaction of like, these numbers are only imaginary, they don't actually exist, so why do I have to study them if they are only in my mind? They are not real things. But here's the thing, all numbers are imaginary. No number is a concrete thing that you can touch. The real numbers only exist in your head as well. You can also think about the fact that historically, people took a long time to accept talking about negative numbers as something that was actually numbers and not just a figment of your imagination, because negative things don't exist in real life. And even rational numbers. The fact that you have the Pythagorean theorem and that a lot of times the hypotenuse of a triangle is not going to be a fraction. Of course, I don't really know this because I wasn't there, but people say that this blew people's minds for a while. That a number that couldn't be written as a ratio couldn't possibly be anything other than a figment of your imagination. And here we are talking about complex numbers and imaginary numbers today. They are also figments of our imagination in the same sense as all of these other numbers are. It's a good thing our human brains have the capacity to think about things that are not like concrete objects in our hands. So anyway, before we start looking at questions, I want to mention one more thing that in terms of notation comes up a lot, so I better tell you about it. So back when all the numbers were in the same horizontal line, if you had a number a here and I asked you about minus a, that would be the reflection, right? The minus a would be on the other side. And if a number, say b, started on the left, then minus b would be the reflection to the right. But now that we have a whole plane of complex numbers to handle, it's important really that we stop thinking about the minus as horizontal reflection and really think of the minus as multiplication by minus 1, which is a rotation of 180 degrees. Because when we have a number in the complex plane, z, and we want to talk about minus z, that is not going to be a horizontal reflection, okay? This z is going to be rotated 180 degrees to the other side. That's minus z right there. And that is consistent with the notation, because if you were to put a minus here, then you would have to distribute this minus to both the a and the b coordinates, right? And I guess if you want to think of it in terms of reflection, you can just make sure it's reflection over the origin of the plane. However, weirdly enough, there is another operation that is a reflection on just one particular direction, but it's not horizontal, it's vertical. So if you take z and you reflect it vertically over the axis, you will get to a number that is called the conjugate of z. The usual notation for that is z star. And there is a minus going on somewhere, but the minus is just going only in the b, only in the vertical coordinate. There's going to be more notation that's going to appear along the way as we go through the exercises, and I'm going to make a list here. I just don't want to sit and list a bunch of notation before we even begin because I think that would be boring. So let's begin with this question. You see that the conjugate of z is already appearing there. So he gives us an equation and asks to solve it. Nothing could be simpler than that, right? I'm going to start by multiplying both sides of the equation by this denominator. But in order to continue from here, I am going to have to substitute z for this expression that he's giving me here. It's the same as the Cartesian form a plus bi that we've been working with. It's just calling them x and y instead of a and b. Notice that when I substituted for z, I just wrote x plus yi, but when I substituted for the conjugate of z, then I wrote x minus yi. That is because the conjugate is the vertical reflection. And the reason why I'm writing the y before the I, even though he wrote the I before the y, is because I like to think of the x and y as coefficients. And usually I put coefficients on the left, like 2x instead of x2. That's irrelevant. It's just the way that I like to do it. But I do want to point out that this equation right now looks like it has a lot of letters, but it's actually just two, okay, x and y, because I is not a letter, I is a number. So this last part of the distributive here, I'm doing slowly to point out that the minus with the minus is plus, but the I times the I, which is here, that's going to be -1. Okay, so now that everything is distributed and organized, now I'm going to show you a technique that's going to come up a lot of times, every time basically that you want to solve an equation to find the value of a complex number instead of a real number. This is going to come up every single time. And I almost said that I was going to show you a trick, but I don't like that word because it sounds like it's not a precise thing. But it is. This is absolutely precise and correct. Look, I do have two variables that I need to find, x and y. That's usually too many variables for just one equation. But the thing is that an equation in complex numbers is actually two equations because you have the horizontal part of the number and also the vertical part of the number. So if you separate those two things one from the other in this one equation, then you're going to come up with two equations. Look, this part of the left side doesn't have any I, and this part on the right side doesn't have any I. But this part has I, and these parts have I. So the red ones are the horizontal parts, and the green ones are the vertical parts. Now I'm going to write each one separately. And in the second one, I've already divided both sides of the green equation by I, so there are no more i's. This is just a system of two equations and two unknowns. Let's solve it. So there you go. I've solved the system and I found what the question was asking for. Find the value of x and the value of y. So there it is. X is -1 and y is 2. Right, so question number 2 starts by giving us a generic complex number. Z equals a plus bi. This time he wrote it the way that I like it. And then he says a and b are real numbers. More than that, they are positive real numbers. And then he says arg z is equal to theta. So there's a little bit of notation that I want to mention. That's literally exactly what he just said, right? The arg z is theta. But just so you know, this notation is common, and it means exactly that. Arg is for the word argument, okay? So the argument of a complex number is just the angle that it's making with the horizontal axis, the same angle that we've been talking about. So basically, so far, this question has given us nothing, right? He is establishing notation. Well, he did say that a and b are positive numbers, so we have our complex number in the first quadrant. Show the points represented by something and something in the following Argand diagram. So here's another word. Argand diagram is just the name that the coordinate plane receives when we're looking at it as the place where the complex numbers live. I should put that in my notation list as well. And that's funny, I hadn't ever realized that argon also starts with the letters ARG. I think that's a coincidence. Arg here definitely means argument. So anyway, without even looking at the question, I already spontaneously said that my number Z was in the first quadrant, right? So that's exactly what he wants to check, that I know that the positive values of A and B mean that the number is in the first quadrant. And now he wants me to subtract 2A, but subtraction is translation, and 2A is a real number. So in which direction is this translation going? It's going to the left. I am subtracting a positive number. But it's not any positive number because A is also this distance, right? It's the horizontal coordinate of the number Z. So when I do 2A, I am basically reflecting it to the other side. So remember just a minute ago, I was telling you about Z star, the conjugate that reflects it vertically. And there is no symbol for a horizontal reflection, but that is exactly what this question is doing. It's doing a horizontal reflection, and it turns out to be Z minus 2A. There's no symbol for that. It's just what it is. But we should also use that at this point to make the observation that the Z star is Z minus 2B. It's the same logic as the other one. But anyway, this has nothing to do with the question. The next item says, find an expression in terms of theta for the argument of Z minus 2A, which is this red point. Well, theta goes in the picture here. It is the argument of Z. So there is a little bit of a symmetry that we can see here, right? We also have theta here, but just like in trigonometry in the unit circle, this green angle is not the argument of the red point, because the argument needs to be measured from here to there. This is the argument, so it is pi minus theta. And this question is only 1 mark, okay? So you don't need to explain it. It's just about getting the right answer, because it is a very simple question. At this point, maybe you would ask, do I have to say angles in radians? Yes, you do. It's not 180 degrees, it's pi. Now find an expression in terms of theta for the argument of something else, Z over Z minus 2A. I'm using the same colors here as in the picture so that we don't forget to think visually about these things, okay? Z and Z minus 2A are two numbers in the same circle with related arguments, but not the same, although definitely the same radius. And what we're doing here is division. Division is like multiplication. So according to everything that we have said today so far, division is meant to be thought about in terms of stretches and rotations, and not in terms of translations. So the Cartesian form is not the most appropriate. We should be using the polar form. So what is the radius of the blue number? I don't know. It doesn't matter because it's going to cancel out. So I'm just going to call it R. And here I am using another bit of notation that I haven't mentioned to you before, this cis thing. So I'm going to put it in my notation list here. Look, it's just shorthand because this thing looks very long and it's boring to write down over and over again. So we're just going to go CIS. And this thing can be written as R times cis of theta. Because really, the whole thing is only giving us one little piece of information, which is the value of the angle theta. So there's no need to write it down like that. Anyway, according to what we did in the previous items of this question, the radius of the red number is also R, but the angle is pi minus theta. So that's why I said that the radius doesn't matter, because it's canceling out. And division is the opposite of multiplication, right? So instead of adding that other angle, I'm going to be subtracting it, because if you multiply by a number you rotate in one direction, then of course that dividing, you're going to be rotating in the other direction. So you're actually subtracting the angle. Right, so this is the result for the complex number that he was talking about, but his question was just about the argument. So the argument is just the angle here. It's 2 theta minus pi. Hence or otherwise, find the value of theta for which the real part of that complex number is 0. Okay, so there is, again, notation here. That's not difficult to guess what it is, right? A complex number is made up of two parts. This is the horizontal part and the vertical part, but horizontal was real numbers. So A is the real part of the complex number, and B is the imaginary part of the complex number. Okay, so what are numbers that have a real part equal to 0? The real part is the horizontal coordinate. So if the horizontal coordinate is 0, I'm talking about numbers that are on this axis here. These are the numbers that have the real part equal to 0. And the angles, the arguments of the numbers to be there, it's like pi over 2, or it could also be like 3 pi over 2, or minus pi over 2, and so on. Let's try with pi over 2 first, because that seems like the most obvious choice. Okay, so 2 theta is 3 pi over 2, which means that theta is 3 pi over 4. But remember that I said there were multiple choices of arguments that would make the real part be equal to 0, and that I chose to start with pi over 2 because it seemed like the most obvious choice. But the question does say find the value. He doesn't leave the possibility open for there to be multiple correct answers. It's just one correct answer. So I have to check if this one is the correct answer. So 3 pi over 4 as a value of theta, well, 3 pi over 4 is like here. 3 pi over 4 is in the second quadrant, and my number z, which is the one that has an argument of theta, is in the first quadrant. So that cannot be the answer. So I am going to try again with a different one. I'm going to try negative pi over 2, which was another option that we mentioned. This gives us 2 theta equals pi over 2, theta equals pi over 4, which is in the first quadrant. So this is the correct answer. Okay, the third question seems very similar to the first one that we did. It's an equation. He is basically asking us to solve it. It's a little different because he's not asking us to find z. He's asking us to find p and q, where q is the imaginary part of z, and p is a number that is just in the equation. So a slightly different question that he's asking, but it's going to be the same thing. What you have to know is that an equation in a complex number becomes two equations in real numbers, and then you go from there. So let's do it. We're going to need z squared, which is 5 plus qy squared. We're going to do the special product. This is 25 plus 10qi minus q squared, because the I squared became a minus 1, which gave me this negative sign here. So I'm going to take that, and then I'm going to add it to this iz here. When I multiply I to this thing, I'm getting plus 5i, and then minus q, because again, the I that I'm multiplying is meeting another I there, and they're becoming a negative 1. And then on the right-hand side of the equation, I have a minus p plus 25i. So now I have to organize this and separate it into two equations, one without I and the other one with I. The first equation looks annoying because it is quadratic and has two variables, but the second equation looks fine. It just becomes 10q equals 20, and then q equals 2, which I am then going to substitute into the first equation. And look, I'm not even going to have to solve a quadratic nothing. It's 25 minus 4 minus 2 equals minus p. So p equals negative 19. Please don't forget this technique. Take it with you. One equation in complex numbers becomes two equations in real numbers. And systems of equations become easier to solve when there is one of the equations that only has one of the variables, which, lucky for us, this was the case here. Next question. Now we have two complex numbers w and z satisfying a system of equations. Here is that conjugate again. So yeah, let's go for it. Let's substitute things. I'm going to look for z equals a plus bi, and then I need different letters for w, so c plus di. And I'm going to start substituting things here. W is c plus di. And then instead of dividing by z, I'm just going to multiply both sides of the equation by z right now. So it's going to be 2i over there and then a plus bi. In the second equation, I am going to use the conjugate of z, which is a minus bi. And then I'm going to multiply w by 3 and then subtract that. The right-hand side is just 5 plus 5i. The first equation still has a distributive that I can do, so 2ai minus 2b. This is the 2, this is the b, and the minus is I times I. So apparently I'm going to have a system of 4 equations here. Let me underline each one in a different color to see where the easy place to begin is going to be. In the first equation, I have without I, c and minus 2b, and with I have d and 2a. In the second equation, I have a minus 3c equals 5, and minus b minus 3d equals 5 as well. Yeah, I'm not sure there's exactly a point to begin here that's easier than other strategies, but it's a simple system. And now just to give the final answer to the problem, I'm going to write z as a plus bi and w as c plus di. Okay, so this next question is giving us the numbers in polar form this time. It starts with item A that is just 1 mark. Find the modulus of ZW, and this is another word that I have to put in my notation list. Remember that the argument of Z was the angle, so the modulus is the other part of this thing. It's the modulus of Z. Sometimes they will say it like this, as if it was an absolute value, also means the radius. So how do we get the modulus when we are multiplying two numbers? We multiply the modulus of one of them times the other one, and the answer is 16. Now he wants the argument of the same number, and we're just going to add the arguments of one and the other. He says in terms of k because there is a k here. So there's a tiny little catch here, just to see if you're paying attention, because this plus, like it has always been in the other numbers that we were looking at, but this is minus, okay? So what that means for the Argand diagram is, because cosine is horizontal and sine is vertical, if you have a negative in front of the sign, that means that you are down here. So instead of rotating upwards, you're rotating downwards, okay? It's like a negative angle in the unit circle, for example. So that's what you have to do here. Just put pi over 5, which is the argument of z, and then you're going to put minus 2k pi over 5 because you want to add them, but one of them is negative, so it's a subtraction. I'm not sure if they expect you to factor out the pi, but I did it anyway. Now he says that ZW belongs to the integers. It's interesting to say that it's integers because integers are just very discrete on the line, but that's not the point. The point is that the integers are a subset of the real numbers, so that is all horizontal. What this is saying is that the imaginary part of this W is 0 because we are a number that is on the horizontal, so it doesn't have any imaginary part. That is very similar to that other problem in which he asked us for something with the real part equal to 0 was on the vertical line. And now we're talking about something that is on the horizontal line, which has an imaginary part equal to 0. And the solution is the same. We want to find the value of k. Well, the minimum value of k. This time he is implying that there are multiple answers that make sense, but we want to take this angle and make it into one of the angles that are horizontal. So 0 or pi, or you go around one full circle, 2 pi. And you can go the other way around too, okay? Minus pi, minus 2 pi. It's easy to make this mistake because he did say in the beginning of the question that k needed to be a positive number. But k is not the number of times you're going around. K is just a number that appears in the expression of the angle. the number of times that you're going around, it's also going to be an integer, but it can be a positive integer or a negative integer. So I'm going to call it n, because usually I would call it k, but this time the variable k is already taken. So I can cancel out pi from both sides of this equation. And now I want the smallest positive value of k that makes this expression equal to n, which is an integer number. So k equals 1 doesn't work because it would be negative 1 over 5. And k equals 2 also doesn't work because it would be negative 3 over 5. But I think k equals 3 works because then, yeah, negative 1 is this angle, which has imaginary part equal to 0. So that is my answer. K equals 3. Oh, the question is not over yet because for one more mark, he wants us to use this value of k equals 3, to find the value of zw. So the whole complex number that we were talking about since the beginning. I think the modulus was 16, right? Yeah, 16. Well, the angle is going to be negative pi because this part was negative 1. We did that intentionally with k equals 3. And then there's the pi. So that's the number. That's not the best way to write this number because if you start on 16 and then you rotate minus pi angle, you just get to this side where it is just the real number, negative 16. So this is a better way to write this number. And for 1 mark, I think I would do that because it might be the thing that they're testing. Okay, the next question is giving us a generic complex number in polar form. We don't know anything about it other than the fact that it is not the number 1. So not that number. And the reason why he said that was because he's going to want to put 1 minus z in a denominator, so z couldn't be 1. But the question is about the real part of some number that is not z. So the real part of somebody is equal to 0 when the number is in this vertical line. So what we know about the argument of this complex number is that it has to be pi over 2 or 3 pi over 2, the same ones that we were working with in the other question that wanted real part equal to 0. So it's this angle or this angle and so on, but it can also be the other way around. So I'm going to put plus and minus here. And now we are in kind of an annoying situation because we want to do a division. And we know that for division, polar form is good. And the question did give us the suggestion to work in polar form. But on the other hand, I have a 1 plus z and a 1 minus z here. So that's addition and subtraction, which is more like translation. Okay, so the argument of this fraction is the argument of one minus the argument of the other. But the problem, like I was saying, is that I don't know anything about the argument of an addition or a subtraction. If it was a product, I would just add the angles, but not for addition. There's nothing I can do. So I am going to try now a very stupid algebraic approach. And I say that this is stupid because I wasn't really able to see anything useful in the picture that I drew before. So this kind of thing that I'm going to do now is usually my last resort, is when I don't understand what's going on, I'm just going to blindly calculate. It's my backup strategy, but it tends to work. So here's the thing. I want to kind of rationalize this denominator. I want a real number in the denominator because then it's just division of real numbers. It's not going to do anything with the angle. It's just going to be a stretch in the radius. And the thing that I am multiplying the fraction by here, you can see that I just took the same number and changed the sign of the imaginary part. So now I get to use a special product. It's this minus this times this plus the other thing there. Okay, so this looks horrible, and there was a lot of opportunity for making mistakes along the way. For example, here the distributive that I'm going to do on the numerator starts with 1 plus cosine times 1 minus cosine, which I use the special product for. And then this one is this part, this one is this part, and finally this is just the I sign times the I sign. We could check my calculations for the denominator, but the thing is that the denominator doesn't matter. It's, even if I made a mistake, it's a real number. That was intentional. That's why we are rationalizing the denominator because dividing by a real number is not going to change the argument of the complex number. And here we are only interested in the argument. So this numerator looks horrible, but a lot of things are going to cancel out. There is a minus cosine squared minus sine squared, which is just minus 1. And then there is a 1 here. So 1 minus 1 is 0. This whole thing cancels out. There is a cosine times sine times I and a minus cosine times sine times I. Those things cancel out too. So the only thing that remained in the numerator was 2 sine theta I. And remember, that is divided by a real number, whatever one that is. So the argument of such a thing, well, it's going to be plus or minus pi over 2, depending on whether this number sine of theta is a positive or a negative number. But the thing is that this number only has imaginary part, right? It doesn't have a plus a real part. So it is in the vertical line like we wanted. So it has a real part equal to 0. I guess we didn't even have to be talking about pi over 2 to do this question, but I didn't know that when I started solving the question. We could have just started with this number, and then we rationalized it, simplified it, and figured out that it only had imaginary part. It's worth it to talk about this rationalization a little bit more, because even though the Cartesian form is good for addition and subtraction, and the polar form is good for multiplication and division, there are times, as we've just seen, where you are forced to do one operation with the wrong form of the complex number. So in particular, for dividing numbers in a plus bi form, the strategy is always going to be the rationalization like we just did. So let's do an example with numbers here. So it's the same trick for rationalizing as when you had like 1 plus root 5 in the denominator. You would also multiply it by 1 minus root 5, right? And it's the same trick because this is a square root. I is the square root of somebody. It's just the square root of -1, but it is still a square root. So the same trick is going to work. So you just do this. Be careful with that last part of the distributive because the sign is always going to be surprising. There was a plus 2i and a minus 4i. So plus with minus, you expect it to be minus, but I'm putting a plus because the I times I that is coming from here and here is itself a minus. So that's what changes that last sign over there, okay? Just have to be careful. And in the bottom, something similar is going to happen, but you're using a special product, so it's 2 squared 4. And then you want to do minus the 4i squared. So there's going to be a 16 here, but the I squared is -1, so this is actually a plus. So now you've done it. You have a real number in the denominator, which was the whole point of rationalization. And now you have again a number that is written in the form a plus bi, okay? Just that the a is 14 over 20 and the b is 8 over 20. But we've done what we wanted to do. We've divided two numbers in a plus bi form, and the answer is also a number in a plus bi form. In the particular question that we were just solving, it was a little bit more complicated than that because the a and the b were themselves complicated things. But I want to point out that a mistake that I've seen people do in this question is to know that rationalization is the way to go because it's a division of two complex numbers that look to be in Cartesian form, but then do this 1 plus z and 1 plus z. This is not correct. Of course, as a fraction, you're always allowed to multiply the numerator and the denominator by the same number. So what I'm doing is allowed. And the answer is also going to use the special product. Here is going to be 1 minus z squared and 1 plus 2z plus z squared on the numerator. But the problem is that this is not a real number. So this is a bad strategy for this question. Not that the strategy that we used before was very good, but the thing is that I had tried to draw a picture and I couldn't find anything interesting in the picture that would help me to solve the problem in a better way. But after I had finished recording that, I realized that the reason why that happened was because I missed something in the question. I said that z equals this was just the most generic complex number, and the only thing that we knew about it was that it was not the number 1. But that is not true. We actually have more information here. The number z that we are talking about is a number in the unit circle. It has radius equal to 1. That's why he's only telling us about the argument. So now that I noticed that the number needed to be in the unit circle, I made a way better picture. I could have done this by hand if I was doing an exam, but I wanted to do it here because then I want to show you how it's always going to work. Say this point here is the point z, okay? It's the number z that is in this unit circle. And no matter where I move it to in the unit circle, the rest of the picture continues to do what it's supposed to do. So this is z in the unit circle. This here is minus z. This one is z plus 1 because it had a translation of 1 to the right. And this one here is 1 minus z because it is the minus z that had a translation of 1 to the right as well. So you see that the angle in the middle there is always 90 degrees no matter how I move this picture. This is exactly what I want to show, but I need to actually show it. Just putting the software to do it is not enough of an explanation. Besides, if I was taking an exam, I wouldn't have the software. So here is the picture again. And what I want to show is that that angle in the middle there is a 90-degree angle. That's because, like I was saying, this is z plus 1. This is 1 plus z. His argument is alpha, which is what I wrote down here. Now this is minus z plus 1. So that is the number 1 minus z. And his argument, I'm putting as beta in the picture, but over here I'm writing it down as minus beta, okay? Because this is going the opposite way around. In the picture, I'm not going to put minus beta because the picture is not really complex numbers. The picture is just geometry and a circle and some triangles. And in that context, negative angles don't make sense. So that is the angle beta. But over here on the right, I'm showing you why that 90-degree angle is actually what I want to show. Because I have the argument of 1 plus z and the argument of 1 minus z. I want the argument of the division, which means that I have to take one and subtract by the other, which makes the answer alpha plus beta, which is exactly the angle that I'm seeing in the picture. So I want that to be pi over 2. And I'm going to show that by using very simple tools, basically alternate interior angles. Look at this horizontal line, which is the axis, and that horizontal line, which was the line of the translation. So this angle here is also alpha because they are alternate interior angles. And the same thing is happening here with beta. I just put this blue line here on the side to be parallel to this line because both of them are 2z. And that's interesting because when I do that, I see a geometric figure here, right? This is a parallelogram. So I'm going to need to call this other angle here something else to use the fact that if this angle here is red plus purple, then this one here on the other side is red plus purple as well. And I'm going to do the same thing here by creating a green angle such that this other one on the other side is also green plus orange. And now when you look at this line going through this and this parallel lines, you have another pair of alternate interior angles, which are now the green ones. So this guy here is green. And if you do the same thing on the other side, you find that this one here is purple. So now I'm going to put another line here that is also parallel to something else. This line CK is parallel to the line AF because both of them go in the direction of minus z and then plus 1. Minus z and then plus 1. So those are parallel lines, which means that this green angle also appears over there. This orange angle also appears over here. And this angle here is going to be a right angle because all four sides of this diamond are the same length. They are all length 1. The horizontal ones were 1 intentionally because we're doing plus 1. And these are also 1 because of the fact that the complex number z has radius 1. So when you have a diamond like that, the diagonals are going to intersect in a right angle, which means, among other things, that the red plus the orange angle are also 90 degrees to finish this yellow triangle here. And that is what I wanted to show. Alpha plus beta is pi over 2, which means that the real part of the complex number that we were talking about is 0. Now, personally, I would have probably not done this during an exam, because once I find the answer in one strategy, then why am I going to keep wasting time to find the second strategy? But at home, I just have infinite time on my hands, so it was annoying to me that I wasn't being able to see the geometric solution. And doing this much calculation just feels ugly. I always suspect that there must be a better way when I see something like that. But it was good that we did that. It was good because it got us talking about the rationalization of the denominator, which was something that we really needed to mention here. And since we're back to this page, I also want to mention something else, which is not going to appear in any of the questions that we're doing today, but you have this form of a complex number and this other form of a complex number. Here you have the meaning of all of these letters. A is the real part, B is the imaginary part, theta is the argument, and R is the modulus. But maybe you want to talk about how to convert between one and the other. And some of these things are obvious, like the real part is R cosine theta, and the imaginary part is R sine theta. Now let's try to do it the other way around. You have an A plus BI here, so which means that this is A, the real part, the imaginary part is going up, it's B. This is a right triangle, so here is the hypotenuse. By Pythagoras, it's going to be this. But that is also the modulus of that complex number, right? It's the distance between the point and the origin. So what we have just learned here is that R is equal to the square root of A squared plus B squared. This might come in handy in some situations. And what about the theta, the argument, which is right here? Well, you can continue to look at this right triangle here. And then you have B and A. Which of the trigonometric ratios are you going to look at? It's tangent, right? So the tangent of theta is B over A, which means that theta is the arctangent of B over A. So there you have it. If you have a number in the polar form, you can convert it to Cartesian form like this. And if you have it in Cartesian form, you can convert it into polar form by using this. And finally, here's the last question that we're going to do today. So the question gives us one complex number in Cartesian form and another complex number also in Cartesian form. Says that B is not 0. And then part A just wants us to multiply them. Well, that's easy. I apologize for the double parentheses here, but it's just that I want this one to be for the distributive and the multiplication that I'm about to do. And the first one is the parentheses that was already in the question, just to separate the real part from the imaginary part in this complex number. And speaking of distributive, sometimes when you want to multiply two complex numbers like this, you can already write them down in the order that they're going to stay. So instead of doing first, outer, inner, last, you already know which one of these are going to be real and which ones are going to be imaginary. So sometimes I like to start by just the first and then the last. And after that, I'll do the two that are going to be imaginary, which is this one and that one. Okay, this deserves to be simplified a little bit. It's not going to be too pretty. I guess it's prettier if I put a minus here so that I don't have to have two minuses inside of this parentheses. Oh, and look, it is going to be prettier than that, because if I factor out 1b from this part, then it is b squared plus 1, just like the first term. So there is this nice factored form here. I'm not sure which one of these I'm going to need in letter B. But now that he says, given the argument of this number that I just did is pi over 4, find the value of B, I'm thinking that the last one is going to be useful, because this thing here is a real number. It doesn't have any effect on the argument. So I am really simplifying things a lot if I just have to look at 1 minus bi. And so what this question is telling me is that the argument of 1 minus bi is pi over 4, which is a number that I know very well. I know where he is in the diagram. This is pi over 4. And I know that the real part of the number is 1. So this is 1. What about the imaginary part? Well, if this is pi over 4, then the imaginary part is 1 as well, right? That's what this angle does. But over here, the imaginary part is minus b. So the imaginary part is minus b, which is then equal to 1, and b is equal to negative 1.